Hey, all right. Hey everyone, so I am Hanna Wallach. I am a researcher at Microsoft and an assistant professor in the School of Computer Science at UMass Amherst. For those of you who don't know me, I'm a machine learning researcher by training, but I wouldn't describe my research over the past couple of years as being traditional machine learning. Instead, most of my recent work has been in the emerging area of computational social science. That is, the development and use of computational and statistical techniques in order to study social processes. So, this is really fun, and this shift in direction has given me an opportunity to start thinking outside of the algorithmic boxes that are typically embraced by the machine learning community, and instead to kind of focus on the opportunities, the challenges, and the implications in using machine learning methods and developing machine learning methods to analyze real-world data about society. So, as a result, this talk is going to be about big data, machine learning, and the social sciences. It's a shorter version of a talk that I recently gave at a NIPS workshop on fairness, accountability, and transparency in machine learning, and it's structured around 4 talking points that really lie at the heart of these issues: data, questions, methods, and findings. So the entire version of the talk, the longer version, is available in essay form on medium.com, and it's probably worth checking out simply because it does contain several more examples and references and so on and so forth. All right, so I want to start by looking at a couple of definitional issues surrounding big data, its properties, and its uses. What is big data? So for something so spectacularly pervasive and trendy, I've heard this question surprisingly often. And initially I thought this was because no one knew or at least agreed upon the answer. For example, NSF and NIH, 2 of the biggest funders of academic research on big data, give the following definition. Big data refers to large, diverse, complex, longitudinal, and/or distributed data sets generated from instruments, sensors, internet transactions, and so on and so forth. All right, fair enough. Meanwhile, other organizations, including, in fact, the Obama administration in their 90-day review of big data, refer to Gartner Inc.'s 3 V's definition. And again, I'm sure you've all heard this before, but big data is high volume, high velocity, and/or high variety information assets that require new forms of processing to enable enhanced decision-making and insight discovery. So, nowadays, I think that the reason why we hear this question so often, what is big data, is that some of the most salient properties of big data, as it's commonly construed, make people very uncomfortable. Yet these vague catch-all definitions don't actually highlight these properties. For example, there's really very little in these definitions, especially Gartner's, that distinguishes this new big data from the massive data sets arising in physics, for example. So why are people so worried about big data and not about particle physics? I think there are a couple of reasons. The first is really nicely captured in this alternative definition of big data from a recent article in The Nation by Michelle Chen. Big data is the amassing of huge amounts of statistical information on social and economic trends and human behavior. In other words, unlike the data sets arising in physics, the data sets that typically fall under the big data umbrella are about people, their attributes, their actions, and their interactions. That is to say, these are social data sets that document people's lives, behaviors in their everyday lives. So the second reason is highlighted by this quote by Mike Jordan, a machine learning researcher, taken from a recent talk of his. The issue is not just size. We've always had relatively big data sets. The issue is granularity. In other words, not only do these data sets document social phenomena, they do so at the granularity of individual people and their second-to-second activities. So, why then does granular social data make people uncomfortable? Well, ultimately, and at the risk of kind of stating the obvious, it's because data of this sort brings up issues regarding ethics, privacy, bias, fairness, and inclusion. And in turn, these issues make people uncomfortable because, at least as the popular narrative goes, these are new issues that fall outside the expertise of those aggregating and analyzing big data. But the thing is, these issues aren't actually new. Sure, they may be new to computer scientists and engineers and people like me, but they're not new to social scientists. So this is where I think the world of big data, ranging from machine learning researchers all the way up to end users and decision makers in government and industry, can actually learn something from academic computational social science. One of the things that I love most about working in computational social science is that it's an inherently interdisciplinary field in which collaboration is absolutely necessary in order to make groundbreaking progress. So you need social scientists to provide vital context and insight regarding pertinent research questions, data sources, acquisition methods, and interpretations. And you need statisticians and computer scientists in order to contribute expertise in developing new mathematical models and computational tools. And it's very much the case that interdisciplinary collaboration is hard. I'm not saying that it's not, and it's also kind of time-consuming, but ultimately it produces results that no discipline could have produced single-handedly. In fact, there's even substantial research in social psychology and sociology indicating that rapid breakthrough innovations are best facilitated by bringing together people with really diverse backgrounds. So, as a result, if technology companies and government organizations, the biggest players in the big data game, are going to take issues like bias and fairness and inclusion seriously, they need to hire social scientists, the people with the best training in thinking about these kinds of social issues. Moreover, I think it's important that this hiring is done not just in a token, hire one social scientist for every 100 computer scientists kind of way, but in a serious creating interdisciplinary teams kind of way. So, within computer science, there's a ton of enthusiasm about big data at the moment. And this is totally unsurprising and completely reasonable. We finally have the kind of computing infrastructure that actually supports the storage and analysis of massive data sets. And this makes for some really exciting computational challenges and opportunities. But when it comes to addressing issues like bias, fairness, and inclusion, perhaps we should instead be focusing our attention on the granular nature of big data, or the fact that there may be many interesting data sets nested within these larger collections for which average case statistical properties may not in fact hold. As a machine learning researcher who's done a lot of work in the social sciences, I think this is a really exciting shift in perspective, and actually one that raises some very different and extremely compelling computational challenges. For example, how can we build models for drawing accurate conclusions about large heterogeneous data sets? Can we develop aggregate models, perhaps inspired by ensemble methods, that account separately for these nested, smaller subsets of these larger data sets? Can we do so without violating ethics or privacy concerns? And if so, how can we build accurate models for these diverse nested subsets? So I don't have any concrete answers to these questions because I think they are in fact research questions and they're not solved yet. However, when thinking about the last one, building accurate and reliable models for these diverse nested data sets, perhaps again we should be drawing on the expertise of social scientists who already have significant experience in this area, in part because it's often the case that they want to answer very nuanced questions about social data for which massive homogeneous data sets simply don't exist. So, with a sufficiently large data set, it's often easy to pick out a coarse-grained signal from noise with even fairly simple mathematical methods. Yet discovering finer-grained signals, such as those associated with data about minorities, can actually be much harder. So, the philosopher Luciano Floridi says, this is a matter of grasping which questions are or will be interesting. Ultimately, the big data game will be won by those who know how to ask and answer interesting questions. And this really underscores, again, the need for social scientists who are trained to ask important questions about society. But it also highlights one of my biggest concerns about some of the big data research and development coming out of computer science at the moment. One of the most common driving forces behind big data research is the convenient availability of data sets. In other words, it's really common for researchers or developers to encounter a new data set and then to structure their workflow around it, be it designing mathematical models or developing computational tools. A related but different approach, one that's perhaps more common within academia, is to create some new model or tool, a hammer, in order to solve some abstract problem, and then to search for a suitable available data set, or perhaps several data sets, nails, with which to showcase this tool. Although this is kind of conducive to fast-paced work, these data-first or method-first approaches can actually amplify issues related to bias, fairness, and inclusion of minorities. First of all, it's really easy to immediately zone in on coarse-grained patterns, typically evidenced by the majority, and then concentrate on analyzing those patterns instead of the fine-grained, harder-to-see patterns that may be associated with minority groups. Second, it's also extremely common to focus on those data sets that are readily available, such as, particularly within academia at the moment, such as Twitter data and things like that. But the problem with these convenience data sets is that they typically reflect only a particular segment of society, for example, young people with smartphones. And so, as a result, many of the methods developed to analyze these data sets end up prioritizing accurately modeling that majority over other segments of the population. So as an alternative, I would advocate prioritizing vital social questions over data availability, an approach that's actually more common in the social sciences. Moreover, if we are in fact prioritizing social questions, perhaps this is a good opportunity to prioritize some of those questions that are indeed explicitly related to bias and fairness and inclusion. Of course, putting questions first, especially questions about minorities, for whom there may not be much available data, means going beyond these standard convenience data sets and general purpose hammer methods. But this provides an interesting research and development challenge, because it means you actually get to think really hard about how best to instrument data aggregation and curation mechanisms that then, when combined with really precise targeted models and tools, are capable of elucidating these really fine-grained, hard-to-see patterns. So much of the existing work on fairness and transparency in machine learning, not that there's very much of it, focuses on predictive models rather than models for exploratory or explanatory analyses. And I find this emphasis to be interesting, in part because explanatory and exploratory models tend to be extremely well suited to answering pertinent questions about granular social data. But also because explanatory and exploratory models are a really important precursor to predictive modeling. So the first step when building any kind of predictive model is to decide which features of the observed data to focus on. In other words, to choose appropriate input or output representations. And to do this, we typically rely on existing knowledge, much of which often comes from previous exploratory or explanatory analyses. As a result, the models used to perform these previous analyses and any kind of bias or unfairness in them will necessarily influence the resultant findings and hence the representations that we then choose to use in our predictive models. So when thinking about the ways in which models for analyzing granular social data can exhibit bias or unfairness, I think it's really important to think not only about predictive models, but also about models for exploration and explanation. So when reading about predictive models in the literature on fairness and transparency in machine learning, something that really stood out to me was a repeated discussion on the dangers of unnoticed errors. So for example, if you're classifying usernames into real versus fake, there's a really big difference between a model that's 95% accurate because of noise and a model that's 95% accurate because it totally nails classifying white American names but only achieves 50% accuracy on names from other cultures. This example highlights the importance not only of careful error analysis, but also highlights the fact that fixing any errors that do indeed relate to bias, fairness, and inclusion will result not only in performance gains, but the kinds of performance gains that people, individual people in society, actually care a lot about. So one way of preventing or mitigating errors is to explicitly represent and maintain some notion of uncertainty. For instance, with any predictive model, some predictions will be more confident than others. Moreover, it is likely that those less confident predictions will be about minority subsets of the data. Error bars or some other kind of representation of uncertainty can therefore help with error analysis by indicating when even correct predictions may actually be predicated on weak information. Additionally, representations of uncertainty can also be used by decision makers or other end users in order to identify those decisions that may require additional human input. A lot of current machine learning methods don't represent uncertainty when making predictions. Moreover, even when using methods that do represent uncertainty, it's actually common to just discard that uncertainty. Sometimes this choice is justified by the argument that ultimately a concrete decision has to be made, so representing and maintaining uncertainty is an unnecessary waste of computation. And I think while this may be true for some tasks, I would argue that when building and using predictive models for social data, where the resultant decisions can actually affect real-world people, representing, maintaining, and reporting uncertainty, along with any subsequent decisions, should be standard practice. And a lot of my own research has focused on Bayesian methods for exactly this reason. So very briefly, since I'm pretty much out of time, I want to focus on drawing responsible, fair conclusions for, oops, I skipped some slides, okay. Responsible, fair conclusions for granular social data. So very few computer scientists or engineers would consider developing models or tools for analyzing astronomy data without involving astronomers. So why then are so many methods for analyzing social data developed without social scientists? And I think in part it's because we have really strong intuitions about the social world. And in fact, my colleague Duncan Watts' recent book, Everything is Obvious, addresses this exact point, that humans are really good at using intuition and at rationalizing and at narrativizing. But intuition is often wrong, and narratives are not historical fact. For example, we all possess attitudes, stereotypes, or other cognitive shortcuts that unconsciously influence our understanding and our actions and our decisions. Some of these shortcuts might be positive and just help us get things done more quickly. But some of them, especially towards people different to ourselves, might actually be less positive and helpful. So being aware that these kinds of implicit biases exist and that everybody possesses them, even scientists, is a really important step towards drawing fair conclusions. So again, I would then argue that it's important to actually make sure that if we want to draw conclusions in a fair and accountable and scientific fashion, we should perhaps not be relying so much on intuition and instead be working with social scientists who actually have a lot of training and even do research in the kinds of human factors that influence both the process of drawing conclusions and the types of conclusions that people can draw. So, although I am a firm believer in interdisciplinary teams, it's really likely that most machine learning methods or data science methods will at some point be used by some people, end users, without the involvement of those people who created them. So if we want the people using these methods to actually be using methods in a responsible and fair fashion, rather than treating them as infallible black boxes, we actually need to be focusing not only on publishing academic papers and making research code available, but also explaining our models and tools to general non-technical audiences. And when doing so, I think it's really important to focus on elucidating implicit assumptions and best practices for selecting and deploying these methods, as well as the types of conclusions that they can and can't be used to draw. So in other words, I would argue that if we're really going to treat these issues of fairness, accountability, and transparency seriously, we need a community-wide increase in commitment to the public understanding of the kind of science that we are, as data scientists and machine learning researchers, producing. So with that, I'm going to stop, but I'd be happy to take questions. And the longer version of this is on Medium if you want to go read it.
Thank you very much. I enjoyed this very much. Different type of talk, very substantial. That was terrific. We have time for one quick question. We're starting to really run out of time, and I want to have time for Chris.
Yeah. How in your research do you think about the limits of certainty in the sense of we all want more and more certainty, but you might have a false positive? So how do you think about how to limit, or how do you tell if you've gone too far?
Sorry, can you repeat the very beginning, the very beginning of that?
The limits of certainty. I mean, how do you know when you've gone too far and you think you have too high a confidence, like if you're identifying bad apples, and the consequence of being identified as a bad apple might be severe?
Right, I see. So you're saying, I think what you're saying is that sometimes machine learning methods can make very confident but incorrect predictions. How do you deal with that? That is an awesome question. And it points to something that's related to error analysis, but kind of the flip side of that, which is doing some amount of sampling of your things that you correctly classified and investigating why your model thought to classify those things as that particular class. So looking at features, looking at weights, digging into results. In other words, that kind of next step of kind of figuring out what's going on. And in my own research, I found that that has led me to identify some situations where my model was being unnecessarily confident about things that were simply artifacts of the particular training data set that I had used and stuff like that. So I don't know if there are necessarily any sort of general purpose, like this is going to fix everything kind of solutions, but I would say yes, digging into why your model is making certain predictions, even when those predictions are correct, can kind of help you contextualize the way the model is working and how it's treating certainty.
Wonderful. Thank you very much, Hannah.